ever actually wondered how digital money moves securely without some big bank or CEO standing in the middle? Honestly, it kind of sounds like magic, but I promise you it's just pure math. Today, we're giving you the ultimate dummy-proof guide to understanding exactly what crypto is and how digital trust is built completely from the ground up. Whether you're brand new to this or just brushing up on the basics, you're in the right place. We're going to break down the tech that secures literally billions of dollars in value every single day. Okay, let's dive right into our roadmap. We're going to build this up step by step. First, the journey of a transaction. Then, building a secure block. After that, we'll look at hardware, miners, and rewards. Next up, the 10-minute heartbeat. And finally, work versus stake.
All right, section 1, journey of a transaction. To really grasp crypto, we've got to zoom way in and look at the actual starting point of any movement on the network. Think about this for a second. What actually happens when you hit send? It's such a simple, everyday action, right? You tap a button on your phone and you fully expect money to move from, say, Alice to Bob. But in a decentralized system where there's no central server running the show, how does the network actually know you authorized that transfer? And where does that transaction even go while it's waiting to be processed? Well, here's the exact life cycle. Step 1, it starts with a cryptographic digital signature. Using some pretty complex math, you basically sign the transaction with a private key. This proves you own the funds without actually revealing the key itself. Step 2, once it's broadcasted out there, your transaction enters the memory pool, or mempool for short. Just picture this as a massive waiting room where all the pending, unconfirmed transactions hang out. Step 3, miners, which are just distributed computers all over the network, pick your transaction from this waiting room. And side note, they usually prioritize the ones paying higher fees. They group these into what's called a candidate block. Finally, step 4, once that block is validated, your transaction hits its final blockchain storage. It is permanently etched into the ledger. Boom, done. And that brings us perfectly to section 2, building a secure block. We know these transactions wait in a mempool, but how do they actually get packaged so securely that literally no one can tamper with them later? To understand that, we have to talk about a core concept, the hash. Think of a hash as a totally unique, completely irreversible digital fingerprint. In Bitcoin, they use a mathematical function called SHA-256. It works like this. If you feed any amount of data into it, like it could be a single word or it could be an entire encyclopedia, it spits out a fixed-length string of random letters and numbers. And it is completely unpredictable. You absolutely cannot reverse engineer this fingerprint to figure out the original data. But if you run that exact same data through it again, you get the exact same fingerprint. So it's incredibly easy to verify, but absolutely impossible to fake. But here's the catch. A single block contains thousands of transactions. You can't just list them all out. That's way too inefficient. Enter the Merkle tree. Imagine a Merkle tree as this highly secure cryptographic zip file. It takes the digital fingerprints, the hashes of all those individual transactions, pairs them up, and hashes them together over and over again. It elegantly compresses this massive list until just a single, tiny piece of data is left at the very top. This is called the Merkle root. Now, why does this matter? Because if a hacker tries to change even a single character in a transaction deep inside that block, it completely changes that final Merkle root fingerprint. That instantly alerts the entire network that the block is invalid. So let's look at how this translates into a miner's actual day job. Here's the step-by-step. Step 1, the miner validates the transactions from the mempool. Step 2, they assemble a block header. This header contains that Merkle root we just talked about, a timestamp, the hash of the previous block, which, by the way, is what literally chains them together into a blockchain, and a blank variable called a nonce. Now, step 3 is where the magic happens, brute force guessing. To lock this block, the miner has to run that header through the SHA-255 function over and over, changing that nonce variable every single time. They're just hoping to randomly guess an output that has a specific number of zeros at the front. It's literally pure trial and error math. We're talking millions of guesses per second until someone finally finds that golden nonce. And once they do, step 4, they broadcast that winning block to the rest of the world. Let's transition to section 3, hardware, miners, and rewards. We've been talking a lot about miners zooming through billions of math guesses, but let's zoom out and look at the actual people and the machines doing all this heavy lifting. Because you have to ask, why on earth would they burn all this electricity and buy all these expensive computers? Well, the answer is financial incentives. When a miner successfully guesses that golden nonce and seals a block, they get rewarded in 2 ways. First, they earn a block subsidy. These are brand new, freshly minted coins entering circulation. Second, they collect all the transaction fees paid by the users inside that specific block. This setup brilliantly incentivizes honesty. Attacking the network would require an impossibly huge amount of money and hardware, but playing by the rules, that guarantees a shot at some seriously lucrative rewards. As it turns out, the absolute best way to keep people honest is to just make cheating insanely expensive. And because those rewards are so valuable, this crazy arms race kicked off. Trace this timeline with me. Back in 2009, literally anyone could mine Bitcoin on their standard home computer using just a basic CPU. Fast forward to 2010, and miners realized that GPUs, the graphics cards PC gamers use, could process these math guesses 50 to 100 times faster because they do things in parallel. But the real game changer hit in 2012 with the birth of ASICs. This is the moment mining shifted from a fun little hobby into a massive, industrial-scale operation. Now, an ASIC, which stands for Application-Specific Integrated Circuit, is absolutely wild. It doesn't run an operating system. You can't use it to browse the internet. You can't play video games on it. Sorry, gamers. ASICs perform one single task, guessing billions of cryptographic hashes per second. That's it. And because the network's difficulty is constantly rising to adapt to all this new hardware, miners are stuck continuously chasing better ASIC efficiency. It's the only way they can stay competitive and keep earning those block rewards. Which brings us right to Section 4, the 10-minute heartbeat. Now, here's a totally logical question. If millions of these super efficient ASICs are suddenly plugged in all over the world, wouldn't they just solve those math puzzles instantly? How does the network keep from basically accelerating out of control? The answer to that relies entirely on this number right here, 10. 10 minutes is the literal heartbeat of the Bitcoin network. It's the target block time. The creator of Bitcoin purposefully decided that new blocks should be discovered, on average, every 10 minutes. Why? To ensure a steady, completely predictable issuance of new coins, and to give all the nodes around the world enough time to actually sync up. So how is this 10-minute rhythm maintained? Through something called the difficulty adjustment algorithm. Think of it exactly like a thermostat for the network. Every 2016 blocks, which takes roughly 2 weeks, the network automatically checks in on itself. If it finds that blocks were being discovered faster than 10 minutes, that means there's too much computing power online, so the algorithm automatically turns up the difficulty of the math puzzle, make it harder. But if blocks were found too slowly because, say, a bunch of miners unplugged their machines, the difficulty decreases, make it easier. It's an incredibly elegant, automated thermostat that protects the fixed issuance schedule, no matter what happens in the physical world. Okay, let's move to our final section, Section 5, Work versus Stake. We've talked deeply about mining, which is officially called proof of work. But how do these massive decentralized networks actually agree on what the truth is? And are there other ways to do it? I absolutely love this quote from our sources. Think of it like a voting system, except the voters are computers around the world and the stakes are real money. It really hits the nail on the head. Because blockchains don't have a central bank to verify transactions, they have to rely on a consensus mechanism. Basically, it's a voting system that forces total strangers to agree while simultaneously making it incredibly costly for anyone to try and cheat. And this brilliantly illustrates the two dominant models in the space today. In proof of work, which is what Bitcoin uses, votes are weighed by the physical energy spent and the computational hardware you actually own. You literally have to prove you did the work. On the flip side, we have proof of stake. In this system, instead of burning electricity, validators lock up, or stake, their own crypto collateral. Their votes are weighed by the capital they are willing to risk. If they approve fraudulent transactions, boom, that collateral gets destroyed. This penalty is known as slashing. Let's take a completely impartial look at the trade-offs here, because honestly, neither system is universally better. They just solve different problems. Proof of work offers this incredibly battle-tested security. It has a 15-year flawless track record, and it heavily ties the digital network to physical reality. But as we know, it is extremely energy-intensive and heavily dependent on that expensive ASIC hardware. Conversely, proof of stake is highly efficient. To put that in perspective, when Ethereum switched over to this model in 2022, they cut their energy consumption by 99.95%. It also makes participating a lot easier without buying specialized hardware. However, critics are quick to point out that it risks wealth concentration, since those who already hold the most coins naturally gain the most validating power. Wow, we've covered an incredible amount of ground today, from the cryptographic signature of just one single transaction, all the way up to the massive global energy-driven consensus that secures the entire blockchain. So as we wrap up this explainer, I want to leave you with one final thought. As block rewards slowly decrease over time and ASICs push the absolute physical limits of silicon efficiency, what will the future of decentralized digital trust look like when the network has to rely entirely on transaction fees to survive?
It's a fascinating question, and you can be sure the entire tech world is watching closely. Thanks so much for joining